Let's take a look at analog to digital conversion as well as its counterpart, digital to analog conversion. Now, pretty much our whole world is analog, with the exception of perhaps your DNA, your genetic code. Everything you are immersed in this world is analog. Light levels vary in frequency and intensity. Sound is varying movement of air. Touch is variable. Temperature is variable. So we need to interface our digital world to the analog world. We will do this by representing an analog variable with a digital number, or vice versa, use a digital number to represent an analog variable. Now, the sound card on your computer is a classic analog to digital and digital to analog converter. The microphone input is an analog to digital converter, which takes a varying voltage coming in the input, produced by the microphone, measures it, and spits out a digital number representing that voltage to the microprocessor. In fact, with a bit of programming skills and your knowledge in analog electronics, you can hack a sound card to do all kinds of analog to digital conversion. When using it as a sound card, all that's happening is a microphone is taking, incoming sound waves and converting them into an analog voltage, usually in the millivolts range. What is called the line level input on your sound card is for plugging in other electronic equipment, like a CD player or an iPod, which has a much higher voltage level in the hundreds of millivolts. Now, both inputs read that input voltage and convert the analog voltage into a digital number. So you can literally hook up, say, a thermistor and a resistor across the power supply, creating a voltage divider, which varies its output voltage according to the temperature. And you can then use your sound card and desktop computer as a data logger. It can record the input as a file of some kind. You just have to remember to design your circuit so that the voltage you feed into the sound card doesn't exceed its maximum input voltage. Now, there's been a lot of backyard science performed this way over the years. We're just going to use the more direct approach and use our microcontrollers, which have analog to digital conversion built right in. Your sound card also has digital to analog conversion, the speaker or headphone outputs on your card. Basically, the microprocessor sends a digital number to the sound card, and the sound card outputs a variable analog voltage on the speaker output. Your PIC microcontroller has onboard digital to analog conversion, but interestingly, the Arduino microcontroller in your kit does not. Now, for short form, we'll call it A to D conversion for analog to digital, or D to A conversion for digital to analog. To help understand the A to D process better, let's start with the D to A process instead. Let's say we wanted to produce a 1 kilohertz sine wave. Now let's look closely at one wave. The analog wave is nice and smooth, constantly varying. Digital is either on or off, but we can simulate this wave with digital outputs and a resistor ladder. For example, let's say we had 8 digital outputs, so we can only turn each of them on or off. Now we can make a huge voltage dividing ladder like this with our 8 control lines outputting 5 volts when they're set high. We will assume that the amplifier we have connected to our signal out is a really good amplifier and has infinite resistance. So when we set this output high, these 2 resistors act as a voltage divider, dividing it in half and sending 2.5 volts to the analog output. If we turn on this output, then the voltage is divided among these 3 resistors. 2/3 of the voltage is dropped across these 2 resistors, so 3.3 volts would be sent to our analog output. If we turn on this output, the voltage is divided among these 4 resistors, so 3/4 of the 5 volts is dropped across these 3 resistors, sending 3.75 volts to our analog output. So as you can see, each sequential output sends a slightly higher voltage to the analog output. So here I just did the math for this particular resistor ladder, with 5 volts coming out of the digital lines. I can now send a varying voltage out on the analog output by selecting which digital line to set high. And I can vary that voltage as slow as I want, or extremely fast, right up to digital speeds. Obviously, I can change the output voltage by changing the resistors and or the output voltage coming out of the digital lines. So now let's take a look at our analog output we have produced. We can mimic the wave by stepping the voltage up and down. In our case, the number of steps is limited by the number of resistors in our resistor ladder. If we only have 10 steps in the ladder and we were trying to produce a wave of 0 to 1 volts, then each step would be 0.1 volts. Now this is called the resolution. The more resistors I add to the ladder, the more voltage steps I can add, the smoother the output. The closer the output gets to an actual smooth analog sine wave. Now it'll never get perfect, but it can get pretty darn close if I crank up the resolution. The other aspect of D to A conversion is what is called the sample rate. This is how many times per second we send out a sample of voltage. If we're setting the digital output, say, 1,000 times per second, and our wave is only 100 Hertz, then we can produce a pretty decent wave output. But if we are trying to mimic a 1,000 Hertz wave, then because our sample rate is so low, it will be pretty coarse and not a very good representation of the wave that we're trying to produce at all, right? It becomes more and more like a square wave instead of a sine wave. If the frequency we're trying to output is high enough, we can't represent it at all. We'll skip entire groups of waves and replace it with a square wave. Let's now convert an analog signal to digital. The resolution and sampling rate are pretty much identical, only we're taking a sample of the voltage, not sending it. The resolution can be as low or as high as you like, but obviously higher resolution requires more computing power. If we use 8-bit resolution, that's breaking up our sample voltage into 256 different voltage steps. Now that's a pretty good resolution. Or you could use 2 bytes, 16 bits. You can represent 65,535 different voltage steps with 2 bytes. That's some pretty serious resolution. Depending on what it is you're trying to measure, perhaps 32 bits is justified. That would be 2,147,483,647 steps you'd be dividing your sample voltage by. But perhaps there's some serious scientific monitoring you need to do. I don't know. Both your PIC and your Arduino have built-in 10-bit analog to digital converters. That means you have a resolution of 1,023 minute voltage changes that you can measure. But more important than the resolution is the frequency of the sampling. The faster you sample, the more accurate your digital representation will be. The slower the sample, the faster you degrade the quality of your sample. Because basically, the slower your sample rate, sampling a higher frequency, the more it converts those nice analog waves into square waves. If your sample rate is too low and your frequency too high, you'll miss entire waves and your digital conversion will be basically garbage. This is most evident when you record sound on your computer and you can change the sample rate. The difference between a sample rate of 8 kilohertz telephone quality and 32 kilohertz CD quality is huge, but do some quick math. Even at 8 kilohertz and 8-bit resolution, to sample and save 1 second of sound on your PIC, that's 8,000 bytes of memory, 8K. You only have 1K of memory on your PIC. Your Arduino only has 2K. So you can quickly start to see the huge volumes of data that could be produced just by sampling sound. You can also start to see the huge volumes of data that even, Siri and the other voice recognition technologies have to deal with.